Thank you for your virtual attending in our department. It's very great event for us because we will learn many things about biochar. And we are very happy this morning, and hopefully next time or in the future, you can visit our department or you can visit Banjarmasin, not in virtual, but in real meeting with us. Hopefully, we in the future we can also collaborate in research or academic program with our campus, because now we have in our curriculum we have a program for maybe internship or student exchange. Probably next year or maybe in the future we can send our student to your campus to learn about biochar or another research. Terima kasih Bapak dan Ibu yang telah bersedia hadir, termasuk juga di sini Pak Uripto selaku WD 1, kemudian Bapak Ibu dosen kimia dan adik-adik mahasiswa, baik itu dari program studi kimia ataupun dari luar kimia. Kesempatan yang baik sekali, di hadapan kita telah ada Dr. Anurita dari Nottingham University, kampus Malaysia, untuk berbagi bersama kita membahas tentang biochar. Mungkin secara umum banyak sekali juga beberapa penelitian tentang biochar, tapi kita akan membahas lebih detail tentang biochar. Black is the new green. It's interesting topic. Hitam adalah hijau yang baru. Ya, environment friendly material from biochar. Terima kasih. Sekali lagi saya ucapkan selamat mengikuti kuliah umum. Semoga kita bisa mengambil banyak manfaat pagi ini. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Bapak Sunardi untuk pembukaannya. Thank you very much Dr. Sunardi for your opening remarks. So before we start, just a little housekeeping things. We will send you the link for the presence list in the chat feature of our Zoom. Nanti link untuk mengisi daftar hadir akan kami kirimkan lewat kolom chat. Kemudian for you who are the students of Chemistry Department, Faculty of Mathematics and Natural Sciences, Lambung Mangkurat University, you will have a separate link that will also be sent through the chat feature. Kalau mahasiswa, khusus untuk mahasiswa program studi kimia Fakultas MIPA ULM, terutama mahasiswa yang mengikuti mata kuliah biomaterial, kemudian teknologi tepat guna, dan kimia lingkungan, itu nanti daftar hadirnya ada sendiri deh ya. So for the students who are taking the courses biomaterial, applied technology, and environmental chemistry, you will have a separate link to fill in the presence list. It will also be sent through the chat feature in our Zoom room meeting. Okay, now, so that's all the housekeeping administration stuff. Before we start, I will read a little about Dr. Anurita, because Dr. Anurita in Indonesia, we have a saying, tak kenal maka tak sayang, which literally means if we don't know you, we cannot love you. So it's necessary for us to know just a little about you. Okay, so let me read a short biography about Dr. Anurita. Dr. Anurita received her bachelor degree in civil engineering, environmental from University Technology Malaysia in 2006, and and a PhD in Fuels and Sustainability from Nottingham University, Malaysia in 2013. Currently, she is working as assistant professor in the Department of Chemical and Environmental Engineering, Faculty of Science and Engineering, Nottingham University, Malaysia. Her current research encompasses on biomass and biomass-derived biochar. Key area of research is to characterize biomass and biochar for potential applications as energy, water and wastewater treatment, soil enhancements and remediations, building materials, etc. So, well, we all know that biomaterials are very versatile. It can be applied in many ways. So, and Dr. Anurita will give further insight about it for us. Her research also involves, my favorite topics, natural coagulants and flocculants for treatment of agricultural wastewater, which I think is very relevant to Indonesia right now. Apart from this area of research, she also conducts research related to technology in higher education. For this, web-based interactive applications are used to gauge student attentions and improve students' learning. Okay, so that is her short biography. And without further ado, I'm giving the time to Dr. Anurita. Dr. Anurita, the time is yours. Silahkan.
Thank you, Utami, for a very nice introduction. Just give me a second. I will share my screen first before I start my presentation. Okay, Utami, I hope you can see my screen and you can hear me clearly.
Yep, everything works fine.
Okay, thank you very much, Utami, for a very wonderful introduction of myself. Okay, and I'm very, very happy to be with you all to eventually share about my research area and a little bit insight of biochar, where the topic on today's presentation will be biochar, where the black is the new green that we are going to talk about. Okay, so I would like to eventually thank the universities, the university, I believe I don't say it wrongly, Universitas Lambung Mangkurat. Okay, so for inviting me in on today's morning, and thank you very much for all the participants who are here to eventually listen to my talk on a Saturday morning. So with that, I will move on with the presentation, where today my title will be on biochar. So I'm not really sure how many of you all are working on biochar or have you heard about biochar before or not, but let me just guide you through briefly about biochar and also what are the potential application it has and what is the nature of biochar is all about, okay, in this particular session that we will be looking at. Okay, just as the introduction just now, my name is Anurita and I have a PhD graduated from Nottingham University of Malaysia, and I'm attached to Nottingham University of Malaysia since 2013. And I am from Department of Chemical and Environmental Engineering under Faculty of Science and Engineering, Nottingham University, Malaysia. So this is my email in case you need to contact me. I'm always available for future collaboration and so on. Okay, before I start, let me just introduce a little bit on the university itself. Probably you would have heard about University of Nottingham. Yes, University of Nottingham, actually the main campus is in UK, United Kingdom. Okay, so that is the main parent campus over there. And somehow after that, after UK, they actually opened up one more branch in China. And we have one campus in Malaysia itself. So I will say Nottingham University in Malaysia is the first UK university that actually ended in our Malaysia. So that was the first university, UK university, that came to Malaysia, and we started around in year 2000. Okay, so it has been almost 20 years. So this year it's supposed to be 20 years of celebrating of our campus in Malaysia. But eventually what happened due to COVID and everything, we couldn't have any kind of events that we can actually celebrate our 20 years. Okay, so this is a very big achievement, but you can eventually see from the screen over here, we have Nottingham in UK, China and Malaysia. The common thing is the lake and also the clock tower that is in the building itself. So they have somehow made the landscape, or they made this building to be kind of similar to each other. So I would like to invite you all, if there is any opportunity, please do come down to Nottingham University in Malaysia. If you come to Malaysia, please do come and visit us. I'm very happy to actually host you all around. Okay. With that, I will move into our presentation today. So the outline of the presentation as shown in the screen. Okay, firstly, I will be eventually explaining about what is biomass, what is biochar, because for those who have never heard biochar before or never heard biomass before, I think it's best to eventually introduce a little bit what are those and what is the properties of biochar and biomass that could be actually helpful for our research. Okay, with that, we will eventually move to thermal conversion of biomass to biochar. And we will also look into potential applications of biochar. So there are many applications, so we shall look briefly into all the applications that is currently being researched. Then I will move on into palm oil based biomass and also biochar to give some insights in Malaysia itself. So it could be very helpful for those in Indonesia, because we have palm-based industry that is like, you know, mass production of oil in both the countries. So we are leading the palm oil, right? So what are the biomass that we can actually get from there, and what is the function of biochar and so on. And finally, before I end the presentation, I will just quickly go through a small case study of my research. I have chosen a palm-based or palm fiber biomass, and how that is being produced to become biochar, and also looking at the energy potential. Okay, so this will be my presentation outline. Okay, let me just start by introducing. So everyone knows what is fossil fuels, and we know that currently we are almost 95% depending on fossil fuels, especially in the energy sector. So when we talk about fossil fuels, I think every one of us, we know that it is mainly oil, gas, and also coal. So these are the three main products of fossil fuel. And all of us know that fossil fuel is not renewable energy, and it takes very long to eventually, or million of years to eventually form. Okay, so looking at coal itself, okay, we know that coal is eventually formed when there are dead plant matter that eventually decays and converted into peat. Okay, so actually the origin of this coal is eventually from dead plant, and it decays into peat. Then over time, with high heat and pressure, because of deep burying, the peat is eventually converted into coal. So that is how coal is being produced. First, it starts with the dead plant, it decays into peat. Over time, with intense heat and also intense pressure, because of burying over, more plants or more soil on top of this peat, eventually it gets high pressure and heat. Eventually, this peat will be eventually converted into coal. And all of us knows that it takes millions of years to eventually form. So coal cannot be formed within a day or two, or not even a month or two, and it not form 1 or 2 years. Eventually, it takes millions of years to form. So we know that coal takes a very long time, or million of years to eventually form from dead plant into coal. So this is actually to give an overview of fossil fuel and coal, and how biochar or charcoal are eventually related or connected to coal. So next I will be eventually showing what is charcoal. I believe many of us would have heard what is charcoal. Sometimes we use this black charcoal in our barbecue, for example. So we want to grill, maybe for example, chicken or so on. When we have parties and so on, we will do this grilling. Okay, so we use charcoal, a black carbon, for our barbecue session. Probably if I ask you, do you know how this charcoal is being made? You will know automatically it comes from wood. Okay, so the simple wood that we have is eventually converted into charcoal. So how this process happen? So when you have wood, when you burn when you burn in a very high temperature and there is no oxygen, what will happen is this wood will be eventually converted into charcoal. So I think many of us, we know that how a charcoal is actually formed. So the two key things will be, one, it has to be kind of high temperature, for example, 300 or 400, and oxygen must not be present, because we know that when you have oxygen, what will happen to the wood? Definitely the wood will eventually turn into ash. Okay, it won't turn into charcoal, but it will eventually turn into ash. So these two conditions are kind of very important to eventually convert the wood to charcoal. Next, I will be moving into biochar. Similar thing. Okay, first we had coal that take millions of years to eventually form. By actually having the dead plants that is converted to coal. Secondly, we have wood that is converted to charcoal without the presence of oxygen, high temperature. Similarly, we have biomass. So biomass can be any bio-origin materials. Okay, so for example, plants, it can be agriculture residues, it can be peels, and so on. So biomass is kind of very general term that we have for bio-origin material. So similar to wood, biomass, when you have no oxygen and when you have high temperature, a process called pyrolysis. So this process of pyrolysis is a condition where you subject the material or your substance with a high temperature without oxygen. What will happen is it will convert this biomass into biochar. Okay, so I hope I gave a very simple explanation to eventually know the relationship of biomass, biochar, charcoal and coal. So that is the connection between one to another. So since it is biochar is being originated from biomass or bio-origin materials, so it is eventually called as biochar. It's a short form of charcoal eventually. So the fancy word will be eventually biochar. Sometimes you will hear biocoal, for example. So it's all the same thing. So biochar is actually the black carbon that we actually get from any bio-origin materials, for example, biomass. Under the condition, most of the time, the condition will be pyrolysis. No oxygen, high temperature, it will convert biomass into biochar. Okay. Then we will look into types of biomass. So I mentioned that biomass can be any bio-origin materials. So there are eventually two types of biomass. One is virgin biomass. Secondly will be waste biomass. So let me just guide you through what is virgin biomass. Virgin biomass can be eventually divided into aquatic and terrestrial. So when it comes to aquatic, it can be further categorized into macroalgae, microalgae, and water plants. Okay. Secondly will be terrestrial virgin biomass, which includes grass, wood, and also cultivated crops. The interest over here, or I will say more towards my research or some of the research that is going on elsewhere, will be more on waste biomass, where you can divide them into municipal waste, agricultural waste, and also industry waste. So when we talk about municipal waste, it can be considered, or it can be classified into sewage sludge, solid waste. Okay. When we talk about industrial waste, we have sawdust that is coming from the wood industry. We have waste oil. Then we can eventually have agricultural waste that includes a lot of palm waste, rice husk, and also fruit peels. So I'm just putting 3 types of waste under the agricultural waste, but eventually all the waste that is come from the agricultural field, we can eventually classify them as agricultural waste. So for example, we are planting corn, for example. So once the corn is being harvested from the plant, what will happen to the plant? So if it's no longer being in use, sometimes what we'll do, we'll just chop it off and then we'll discard it, or sometimes we'll do open burning to get rid of the waste. So the stalks, the corn stalks are eventually considered as agricultural waste as well. So just imagine, for example, taking Malaysia and Indonesia as an example, we having quite a lot of agricultural waste that is not being tapped, because we do plant quite a number of things, fruits, vegetables, and crops, and so on. But once you harvest the fruit, or once you get your product, sometimes what will happen to the waste is eventually it just, sometimes we burn it, sometimes we just discard it in the landfill. So all the waste that comes after the fruit is being harvested is eventually waste that could be eventually potential for any other uses. Okay, so that are agricultural waste. Okay, and we might be actually asking, why are we choosing biomass, or why are we choosing biochar for our research purpose? So number one will be for its availability. Okay, looking at many developing nations, for example, if I take Malaysia as an example, or taking Indonesia as an example, we do have this biomass that is abundantly available, okay, in the agricultural countries. So it is available there, it is abundant, but sometimes we are not tapping its potential eventually. Okay, so one is the availability. Second is probably we want to have waste reduction. Okay, how can we actually reduce this waste is by minimizing the waste that is ending in the landfill. So if we are not doing anything with the waste, sometimes what will happen is we are just discarding and it will eventually end up in the landfill. So what will happen? Landfill will get more and more occupied. Okay, once it's more occupied, the capacity is not there. So by minimizing the waste or reducing the waste, in the future, it can eventually reduce the number of landfills in the country itself. Okay, so thirdly, we want to look at the environmental side of it. We want to reduce the environmental pollution. So how environmental pollution is being reduced from using, for example, biomass or biochar as our research part, or when it's applied in some other kind of application. So you know that we have biomass. Biomass is actually waste, agricultural waste, for example. This agricultural waste, especially plants, okay, what will happen is when they are growing, they eventually absorb this carbon dioxide during their growth. Okay, so they absorb the carbon dioxide when they are growing. Meaning to say, we know that carbon dioxide is a greenhouse gas eventually. So when plant take in carbon dioxide during their growth, and when they decay, they will eventually release back the same amount of carbon dioxide through decaying process. So that is why biomass is eventually considered as carbon neutral, meaning to say whatever it absorbs during growth, it will release those particular CO2 to the atmosphere. So it doesn't contribute additional CO2 emission to the atmosphere. Okay, so that is number one, CO2. Number two will be, we will have reduction in greenhouse gas emission. So we are looking at methane now. Methane, as we know that methane is eventually another greenhouse gas. So how methane is being contributed to the environment is through decaying process. Okay, so when a material, a biomass, for example, if it decays, it will eventually produce methane as well. But if we convert this biomass into biochar earlier itself, before it goes through the decaying process, we are eventually eliminating the methane that will be produced during the decaying process. Okay, so these are the three important criteria, or three important benefits of eventually using biomass and also biochar before it decays. Okay, so we already have a very a brief idea about biomass. We know about biochar, but we might be thinking, how can we eventually convert this biomass into biochar? Here I am just going to just go through the thermochemical conversion, because ideally we can eventually convert this biomass to biochar through biological conversion as well. But what I'm going to do here is eventually explain a little bit more on the thermochemical conversion, because I have been working on that. Okay, so looking at thermochemical conversion itself, we have quite a number of processes. Okay, you would have heard about combustion, you would have heard about gasification, you would have heard about pyrolysis, and probably you would have heard about liquefaction. Okay, so let us just briefly go through what each thermal conversion process does. So for example, firstly, we look into combustion. So this is eventually a chemical process where a substance, it reacts rapidly with oxygen and gives off heat. Okay, so any kind of substance, when you burn them, okay, you have a lot of oxygen around you. So when you are burning them, what you will be getting is eventually intense heat. Okay, heat can be actually used as a source of energy as well. But what will happen when you are burning with oxygen is you might be having a lot of ash, because that will be one of the main byproduct that will be coming from combustion. Okay, so sometimes this ash is not desired. Sometimes it can be eventually converted into some other material that will be actually helpful in some other application. But here I just want to compare one thermochemical conversion process to another. So that is combustion. Combustion always happen when you have excess oxygen. Okay, it will change our material to ash. Okay, and it will give a lot of heat that can be used in the energy sector, for example. Okay, so that is combustion. Secondly is a process called gasification. So the name itself shows that gasification is the process where we want to have syngas as a byproduct. Okay, so there are a lot of research that is being done on gasification. So ideally the whole process is eventually like this. When we have a substance, for example, taking biomass as an example, or biochar as an example, so our substance will be kind of reacted to gasifying agent. That means it needs some other agent to eventually induce this gasification process. So most of the time, the gasifying agent that will be used are, steam, air, and also carbon dioxide. So either one, when it is used on this particular biochar or biomass, what will happen is this substance will react to the gasification agent. Okay, the end product will be syngas or gaseous products that will be eventually produced. Okay, so there are a lot of research being done for gasification. The main aim of gasification I see nowadays is eventually to produce hydrogen rich gas. So why hydrogen? Because many people are eventually doing a research and we are depending on fossil fuel. So people are actually moving towards alternative energy or renewable energy. So hydrogen is eventually another alternative energy that we can have. For example, we can use in the fuel cell and so on. But these are more on research scales that is being involved. Okay, so gasification will be very much important when we want to actually get syngas, especially when it's hydrogen-rich syngas. So that is gasification. Next, I will just move into this liquefaction. Okay, so the depolymerization process is used to convert biomass into crude-like oil or bio oil. So here, when the conversion is eventually you use biomass, but the main intention will be to produce bio oil or bio crude under the moderate temperature or high temperature. All right, so here the intention will be kind of to get bio oil for some other applications as well. So that is what we call as hydrothermal liquefaction. Okay, so basically this thermochemical conversion of biomass will eventually happen at high temperature. Okay, so gasification usually it requires a temperature of more than 600, and even liquefaction it needs a moderate temperature, maybe 200-300, high pressure. Then finally we have something that we call as pyrolysis. So I'll be focusing on pyrolysis in my coming slides because that is the focus of this particular talk. Okay, so this pyrolysis eventually we can divide into slow pyrolysis, intermediate pyrolysis, and also fast, or we call it as flash pyrolysis. Okay, so the product that we'll be getting from the pyrolysis are bio oil, gases, and also biochar. So you see biochar over there, that will be our main focus. So through pyrolysis process, we can eventually get high yield of biochar. Okay, looking at pyrolysis, so you might be asking, what is pyrolysis? So pyrolysis is the conversion of biomass. Okay, so we are converting this raw biomass or raw agricultural waste that we have, okay, by heating up at temperatures ranging from 300 to 350 to around 900. So the key thing over here is in the absence of oxygen. So as I mentioned, when we have oxygen in our reactor or so on, what will happen is it will burn our biomass completely, leaving us with only ash. We do not want that. So when there's no oxygen, when it's inert atmosphere, okay, what will happen is eventually the biomass will be converted to biochar. So you see the temperature range is eventually very wide, 300 to 900. So how do we eventually choose the right temperature for the right biomass that we have? So this is what research involves eventually. So what will be the optimum temperature that gives you the desired yield or desired quality of biochar that you might need? Okay, so the product of this pyrolysis of biomass will eventually three things. One is the bio oil, secondly is the biochar, and thirdly is the syngas, which also have hydrogen, methane, carbon monoxide, carbon dioxide, and so on. Okay, so these are the three products that will be coming from the pyrolysis process. Okay, biochar is the solid product, bio oil is the liquid product, and the syngas is the gaseous product. Okay, so that is pyrolysis. Then we move on to the type of pyrolysis. Okay, as I mentioned in my slide just now, we have three types of pyrolysis. One, we call it as slow pyrolysis, or the most conventional one. Secondly is the fast pyrolysis. Thirdly is the flash pyrolysis. So looking at this method itself, we can actually see the difference between or different operating condition between these three pyrolysis method. So most obvious one will be the temperature, the residence time, and the heating rate. So these three parameters, or the operating parameters, are kind of important to eventually decide the method that we are going to use. Okay, so for example, we have slow pyrolysis. The temperatures are medium to high. We use around 400 to 500. Residence times will be like, okay, once you heat up to that particular temperature, how long do you or do we want to hold that particular biomass so that the reaction can happen? Okay, so heating rate, on the other hand, is how fast do we want to heat up our sample to the targeted temperature. Okay, so looking at the table that we have now, so we can eventually see at the temperature, okay, from conventional to fast to flash pyrolysis, actually the temperature are increasing. So slow pyrolysis happens at roughly lower temperature compared to fast pyrolysis, and also flash pyrolysis. And when we look into this residence time, that means how long are we holding our sample, we do have slow pyrolysis. We are holding the sample for quite long compared to fast pyrolysis, and flash pyrolysis is very short, just a while we are holding. Then the heating rate will be slow pyrolysis. You heat up the sample at a very slow rate compared to fast and flash pyrolysis. So what are the major products that we have? So overall, we do have char, we have oil, we have gas, but the proportion or the yield of this char, oil, and gas differs from one to another. So at the last column over here, you can eventually see the yield. For example, for slow pyrolysis, the char yield is around 35%, the gas yield is around 35%, and bio oil is around 30%. And for fast pyrolysis, what will happen is char will be around 20%, oil is around 50%, and gas is around 30%. And for flash pyrolysis, you can see the char yield is 12%, the oil yield is 75%, and gas yield is around 13%. So you might be thinking which will be kind of relevant for, or the most appropriate one for biochar. Looking at the yield itself, slow pyrolysis or the conventional pyrolysis eventually gives more char yield compared to fast and also flash pyrolysis. Okay, so most of the time slow pyrolysis will be kind of adopted to produce biochar that we want. Let us just move a little bit on this mechanism of this pyrolysis. So these are the three mechanisms, the basic mechanism or the basic reaction that happen in the biomass itself. First, when you have biomass, biomass will be eventually converted to water plus unreacted residues. It's called as pre-pyrolysis. Then secondly, we have this primary reaction. Third is the secondary reaction. So let us just look what happened during pre-pyrolysis, primary reaction, and also at the secondary reaction. Okay, let me just move on. So during pre-pyrolysis, what will happen is this moisture or the water will be kind of eliminated or evaporated from the biomass structure. So mostly this will be like when we are heating up, when it reaches a temperature of around 110, most of the moisture will be kind of eliminated from the biomass structure. So that is the first step or the first stage where pre-pyrolysis happens, where the elimination of water happens. Then during the primary reaction, okay, the unreacted residues will be eventually converted into volatiles and also gases together with char. So this process is eventually called this devolatilization process. So here it includes the dehydration, decarboxylation, and also dehydrogenation process that eventually occur during this primary reaction. Then lastly, we have the secondary reactions. So the secondary reactions always refers to the cracking of heavy organic compounds as well as the repolymerization and issues. It produces a stable and carbon dense solid product. So the final product is the biochar that we are looking at. It is a carbon dense. That means this product is highly or rich in carbon. Okay, and we also have some other non-condensable syngases. So for example, what are the gas that will be produced is methylene, methane, carbon monoxide, and carbon dioxide. Okay, so these are the example gases that comes out from this pyrolysis process. Okay, so this picture eventually shows pyrolysis reactor, for example, probably in a more larger or commercial scale and so on. So eventually it shows what are the feedstocks that we can eventually put in. Okay, so we have quite a number of feedstock that is shown in the picture over here. So it can be any kind of bio-origin material, as I mentioned. It can be rice husk, it can be animal manure, it can be agricultural waste, it can be wood chips, and so on. So all the feedstocks, or not all the feedstock together, but eventually the feedstock that you're researching on can be supplied to this pyrolysis reactor. Okay, when pyrolysis process happen, okay, it will produce bio oil and also gases. This biofuel, or especially the syngas that is produced, can be eventually used for transportation, energy, and so on. Okay, So what is the outputs that you'll be getting? So beside biochar, you can also get energy, okay, in terms of syngas and also bio oils. All right, these can be actually producing heat, power, or combined heat and power. So a reactor, we are looking at a large scale or commercial scale, eventually give the energy that is required. So what happens to the biochar? Okay, later I'll be showing you what are the applications that we have. Now some of the focus are moving into applying the biochar into the soil to see or improve this crop growth. All right, so this is the biochar production. Then looking back at biochar, you might be asking what's the difference between biochar and also biomass. So biochar is the solid product from pyrolysis of biomass. And most of the time, compared to biomass, since it's being converted into a solid carbon, the carbon content in the biochar will be kind of increased to around 70 to 80%. And it is highly porous. It has low bulk density, highly aromatic, and this biochar is a versatile material for various applications. Okay, so this is the conversion to biochar, and these are the properties that the biochar has, and this biochar can be applied in various applications. So this picture eventually shows the conversion or the porous structure of the biochar under the SEM image. So we can eventually see the biochar has a porous structure. So this structure itself eventually is like very beneficial for all kind of applications. So most of the time, people do, for example, do research on wastewater treatment. So this porous structure will eventually create active sites for the adsorption to happen. So for example, if a research is on absorbing heavy metal from wastewater, so this structure eventually aids the adsorption process to happen eventually. So the uniqueness of this biochar, which has this porous structure, eventually helpful or benefiting in many applications. Okay. Okay, let us just move into the properties of biomass and biochar. So when it comes to biomass and biochar, most of the time we will be looking into the characteristic of this biomass and also this biochar. So what are the properties? The first properties that we look into is we'll look into the moisture content, we'll look into the volatile matter content, fixed carbon content, ash content, and also heating value. So what is moisture content? So we know that moisture content is the water molecules that bond to the materials. Okay, so when we have a biomass or a biochar which has high moisture content, okay, it might not be desirable, for example, taking into account and for an energy application. Okay, so if the moisture is high, definitely we can actually conclude that it will have poor ignition. Okay, so for example, moisture content higher than 30%, it will have a poor ignition. So when it has poor ignition, it also reduces the calorific value. So the calorific value that we are referring to is eventually the last part here, heating value. Okay, so there are a few terms we use. I mean, calorific value is eventually same as heating value. Eventually, one is calorific value is the energy content in the material itself. Okay, so moisture content is very important especially for energy application, because high moisture content will reduce the calorific value, meaning to say there's no purpose for the biochar or the biomass to eventually use in the energy application. So if we compare biomass and biochar, okay, biomass is not full, I mean, it is highly, I mean, there's high water content in the biomass. What will happen when we eventually put in the pyrolysis process, for example, by converting to biochar? Okay, we had a pre-pyrolysis stage just now where water elimination process will be occurring at a temperature of more than 100, at a temperature of more than 100. So this water will be kind of evaporated. So this biochar that we are eventually getting, the moisture content in the biochar will be so much reduced compared to the fresh biomass that we have. So that is on moisture content. Second is this volatile matter content. So the volatile matter content is the volatile compounds that is being released when the material is heated up to a temperature of 950 degrees Celsius. So we have a sample now, we are heating up to 950 degrees. So our material will be starting to react and eventually it will release all this volatile compound. So when we heat 950 degrees Celsius, all the volatile matter compound will be fully released. So we can eventually measure what is the volatile matter content in the biomass or biochar when it is reacted at 950 degrees Celsius. Okay, fixed carbon content on the other hand is the carbon fraction that remains after all the volatile compounds has been expelled. Okay, so when we heat up a biomass to a particular temperature, for example 950, first what will happen, moisture will be evaporated at a temperature of 100. Okay, and slowly we are heating up more, all the volatile compounds will be releasing up to 950. So 950, when all the volatile compounds are being released, the remaining fraction will be eventually the carbon that remains in the material. So why carbon is actually very important, especially when it's going to be used in the energy sector. It provides a measure of how easy the material can be ignited if it's used as energy. So we can say that most of the time when the biochar has high carbon content, the calorific value or the heating value of this biochar will be kind of more, meaning to say it has more energy content in the substance itself. So when it is used in the energy application, it can easily ignite and can be used as a source of energy. So that's why fixed carbon content are kind of important, especially in the energy sector. Finally is the ash content. So ash, as we know, is the presence of inorganic constituents such as organically bound cations, inorganic salts, and also mineral. So I did mention just now that heating value or the calorific value, both are actually referring to the same thing, is the energy content of the material. So how much energy a material has. So most of the time, moisture and fixed carbon content will affect the heating value. As I mentioned just now, moisture content will reduces the calorific value, whereas increasing carbon content will eventually increase the heating value. So from the pyrolysis process, by converting biomass into biochar, we are reducing the moisture content, we are increasing the carbon content that will be kind of needed especially for energy application, the heating value that is required. Okay, so this table now eventually shows this proximate analysis. So when we characterize this biomass and biochar, what will happen is we will try to do proximate and ultimate analysis. So what is proximate analysis is determining the moisture content, volatile matter content, fixed carbon content, and also the ash content of a particular biomass or biochar. So the table over here, I just took from the literature all these values, all right, for the biomass that has been used. Okay, what are the moisture content, what is the volatile matter content, fixed carbon content, ash content, and so on. So we can actually see from the table over here, there are so many biomass that is being used, okay, from almond shell to bamboo to coconut shell to corn cob, corn stalk. The table doesn't end here. We have a continuation of, in the second page, we have oil palm EFB, we have PKS palm kernel shell oil palm, wheat straw, and so on. Okay, so we need to say we have abundantly available biomass that has been researched eventually. Okay, with the research that has been done, this table eventually summarized the proximal analysis for each of the biomass that is being researched. Okay. So that is proximate analysis. So the second one that is important will be to know the ultimate analysis. So what are ultimate analysis? Ultimate analysis, on the other hand, is the elemental composition of the biomass or biochar. So what is elemental composition is the For example, a biomass or biochar, it will have carbon content, it will have hydrogen content. So in this table, the C, H, N, O, and S represents carbon, hydrogen, nitrogen, oxygen, and sulfur content. So these are the basic characteristic or properties of biomass that a biomass will have eventually the content, the carbon, hydrogen, nitrogen, oxygen, and sulfur. So this table eventually summarize some info that we found in the literature. Okay, so we can actually see what is the variation like for biomass. Okay, so this is the second table, the continuation of it. All right, so that are the important parameters of, important properties. Let me just move on to the biochar characterization. So how do we characterize the biochar? We will eventually look into the chemical property. So I'm just going to go fast on this because these are just mentioning what are the analysis and what is the equipment that we actually use for the analysis. So first will be to determine the chemical properties. So we always try to use or we will try to characterize the biochar. What is the pH like? What is the electrical conductivity? What is the cation exchange capacity? That will be more on for application in the soil. Okay, later we'll look at it. Biochar composition. So composition, usually we use CH and S analyzer. The ash content, the proximate analysis, the surface functionality, surface acidity and alkalinity, surface aromacity. So these are the chemical properties typically a biochar will need to be characterized for. But the most important will be probably the proximate analysis over here that I mentioned just now. Then we have physical properties such as determining what is the surface area, what is the pore volume and size, what is the particle size distribution, what is the density. Okay, the one in the bracket is eventually the method or the equipment that we use to eventually do all these property studies. Okay. Then thirdly, we have surface structure and morphology. Here we use SEM, scanning electromagnetic analyzer. Okay, then we have TEM, which is transmission electron microscopy. Crystallity, we use XRD to eventually see what is the surface structure and morphology. Then finally, we will want to determine what is the behavior, stability behavior. Usually we use a thermogravimetric analyzer. Okay, so this is how we characterize the biochar. So the most important part will be on the applications. Okay, so as I mentioned before, there are various or versatile applications for this biochar. Probably some of you are already working on this particular area, but let me just quickly go through what could be the applications of biochar that we have. Okay, number one will be on waste management. So as I mentioned, we have a lot of waste, we have a lot of biomass, but if it's not tapped to the potential, it is just going to decay and create more problems to the environment and so on. Okay, so there are a lot of research that is being done to actually manage this kind of waste so that it can be kind of upgraded to a useful material, or it can be something that can be done to actually manage this kind of waste. So the proper application that I would like to highlight over here is the energy application. So for the past 10 years, there are a lot of research that moves towards energy, biochar for energy applications. Okay, how biochar can be applied in the energy sector. Okay, so as I mentioned in my first slide, if you see, we are highly depending on fossil fuel, which is oil, which is gas, and also coal. But we do not know how long all these things can last. And if you see, coal actually takes a million of years to eventually form. And if we see coal, charcoal and biochar, they are eventually connected because they are actually coming from the same plant material, for example. Okay, but it's just the time taken for them to be formed are kind of different. So coal, million of years, whereas you can get your charcoal and your biochar within 2 hours, for example, if you're doing the in the lab. Okay, so but the conditions are the same. You are applying or we are applying a condition where no oxygen, high temperature, which will convert these plants or biomass to biochar. So as a solid product, biochar, it can become a solid fuel eventually. So once the biochar is being produced, if we can actually burn it again as a source of energy, okay, meaning to say this solid product can be used as a energy as itself, because the calorific value has been increased. So definitely it has a better energy content in the biochar itself. So the question comes is whether this biomass or this biochar that is being converted, whether this biochar has the same calorific value as coal or not. Okay, coal roughly has around 30 or 27, sorry, 30 megajoule per kg. Whereas most of our research that I have seen or in the literature, when biomass is eventually upgraded to biochar, the energy content is around 20 something, 25 megajoule per kg and so on. Okay, although it doesn't reach up to the coal's energy content, but somehow it has been upgraded from, you know, typical biomass is it has around 15 megajoule per kg, for example, but it has been upgraded into something more calorific value, okay, which can be a substitute of coal as well, depending on how much we have the availability of biomass and the conversion to biochar eventually. Okay, so that is on the solid. Secondly, on the oil and also on the gas, basically when we are converting from biomass to biochar, I did mention that we have bio oil, we do have gas, and even gasification process produces syngas as well. Okay, so all these gases or the oil that is coming out from this pyrolysis process or gasification process or even combustion process, what will happen is eventually it can be used in the energy sector. Okay, it can be used as a source of energy, but it's not widely being used. Okay, in certain industries, okay, certain plants. Biomass has been actually used as a source of energy. Okay, so that is on energy. Secondly will be on climate change mitigation. So you might be wondering how biochar can be helpful in climate change mitigation. Okay, so the first one will be in terms of reduction of methane, and also since biomass is carbon neutral, so somehow it will eventually reduce the CO2 and methane without going through the decaying process. But there's another area or another emerging field nowadays where carbon or the biochar, okay, it has the ability to eventually absorb the CO2 from the surrounding. Okay, so there are, I did came across like a few papers or current research. Okay, what people do is they have biochar. Okay, when they inject CO2, this biochar has the ability to eventually absorb and store the CO2 in the biochar itself. So just imagine when we have biochar and it can absorb the CO2 around us, it is actually acting as a carbon sequester material. Okay, so basically carbon or the biochar absorb the CO2, and most of the time what will happen is people do put it in the soil as a carbon storage, meaning to say once it absorbs the CO2, it is being stored in the soil for don't know how long, because it has the ability to capture and store the carbon. Okay, so it can help as a carbon storage material itself. So that is how the climate change is kind of like, we can avoid this climate change mitigation through carbon capture potential that biochar has. So this is one research. Some other application will be, I think probably we would have known quite a lot on soil remediation and wastewater treatment. So basically these are more common. Okay, for example, if you're taking even wastewater itself, there are a lot of heavy metals. Soil remediation and wastewater treatment comes some sort together, because most of the time when we talk about heavy metal can contaminate this, it comes in the wastewater, or it can eventually contaminate the soil itself. Okay, so for example, we have lead, mercury, nickel, and so on. There are so many heavy metals from different processing industry. We have all this heavy metal that is found in the wastewater that can eventually go to the river or sea or so on, and it can also seep through the soil, where the soil can become contaminated as well. So how this biochar can help is eventually it has the ability to absorb all the heavy metal. Okay, so this biochar application in the wastewater treatment and also for soil remediation has been like I mean, very much being researched. Okay, so the important or the next important part will be biochar as soil conditioner. So these are emerging as well, because there are a lot of studies that found that biochar has the ability to condition the soil. Okay, condition meaning to say it can improve the soil carbon. Okay, it improves the soil fertility. How? It can eventually lock all the nutrients, it can hold all the nutrients in the biochar. Okay, it can also become a house for the microbes to eventually do their work in the soil. Okay, and it can actually help to hold the water, so it has the water retention capacity. So what happens is in many studies, when this biochar is applied in the soil, it actually helps to hold the nutrients, it conditions the soil, and by conditioning the soil, it can eventually help in terms of crop growth. So there are more healthy plants, there are more healthy crops. Maybe the production is kind of increase as well. So that's what biochar can do when it is applied in the soil conditioner. So these are the main main application that we can eventually find in the literature. But there are some other simpler research that can be actually used. Nowadays, I mean, I did came across a few research where they use as additives in composting. Okay, so we know that composting takes quite a long process. Sometimes it takes 3 months or 4 months or sometimes 6 months to eventually fully decompose food waste, for example. So what happened is they actually add biochar during the composting process. So this biochar has the ability to hold the microbes inside it, so it can eventually accelerate the composting process. Okay, so that has been used in composting. I did come across where biochar has been used in as additive in the cement industry. Okay, so when biochar is being applied as an additive in the construction material, for example, what happens is the strength, okay, the flexural strength or the compressive strength of the material are kind of enhanced or better when biochar is being added. So in the construction industry, you know, when biochar has the carbon capture abilities, and if we can eventually capture the carbon or carbon dioxide in the biochar, then apply in the construction industry, so it will be a better or ideal solution for CO2 capture as well. Some other researchers also include in the supercapacitor application. So biochar has been used in the supercapacitor application itself. So we can eventually see there are wide scopes that a biochar can be applied for. So there are so many areas that people can work on. So it's a very good, I will say a good approach where we can eventually take biochar as a potential application in whatever field that we are actually working on. So these are some of the applications that I found. Let me just move into some of the perspective in Malaysia. So what are the biomass that we have in Malaysia? Okay, so this is the percentage of biomass or the waste that is being generated in Malaysia. So if we see, most of it, or 86.18% of it, are palm oil based biomass. I'm not really sure of situation in Indonesia, but I believe as a leading palm oil distributor or manufacturer, we would have a lot of palm oil based biomass that is available in our country eventually. So the other smaller fractions will be, 5% is municipal solid waste, 3% is woody biomass, paddy is around less than 2%, and others is around 4%. So looking at it in a year, we have around 80 million tons of solid biomass from the palm oil industry itself in every year. So I will just go through the palm-based biomass in Malaysia, all right, because I just selected that as because that's the most available or abundantly available biomass in Malaysia. Okay, so just looking at this particular diagram, we can note that we are getting palm oil from oil palm tree. Okay, so when we harvest the fresh fruit bunch to be processed in the palm oil mill, what will happen is eventually only 10% of the mass weight will be eventually be produced as oil, and 90% of the remainder are eventually created as biomass. So we can actually look into these two. One is the plantation residual and also palm oil mill residual. Okay, so once the fruit is being harvested, in the plantation itself, we have oil palm fronds as our residual. We have these fresh fruit fronds sometimes as residual. It's not residual, but that will be eventually sent to the palm oil mill for further refinery. And we have this oil palm trunk as a residual itself. Okay, so this fresh fruit bunch, when it's sent to the palm oil mill, okay, it is being processed to get oil. So what happened after we get the oil? We have palm kernel cake as a waste, we have palm kernel shell as a waste, we have empty fruit bunch, we have the mesocarp fiber. Okay, so the percentage is actually shown over here. So I would say the highest percentage will be for empty fruit bunch. Okay, so the product is eventually crude palm kernel oil and also crude palm oil. And not forgetting, POME or the palm oil mill effluent is a very big residual or the effluent that eventually hazardous as well, that need to be taken care of, that are also waste in liquid eventually. So we have quite a lot of waste in the palm oil mill that can be done something. So what happened in Malaysia is, okay, there are a few companies or spin-off companies that are actually looking into this biomass from palm oil industry. Okay, so this picture eventually shows the whole, the whole process. What do they do with all this waste that is coming out? So not all are actually converted into biochar, but some are eventually turned into some other products like dried long fibers, compost, briquettes, and pellets. So we can eventually see from here, EFB, oil palm trunk, PKS, palm fiber, what they do, what is the conversion technology that they have, and it is being used in the heat and power, energy, in the mill itself. Okay, some are connected to the grid to eventually convert into electricity. One of the main one will be to produce biogas. Okay, so biogas eventually can produce electricity on the other hand. Okay, so and the PKS, especially palm kernel shell, are converted into charcoal, which can also use in the energy system. And recent interest has actually by converting this what you call waste to organic fertilizer. So there's a market for organic fertilizer eventually from the palm oil industry. Okay, so this actually shows some of the waste, for example, EFB, PKS, OPT, the trunks, fronds, cake, and so on, and what could be the products that comes from them. And some are like still on research scale, some are going towards the commercial scale. And when we see biomass or biochar, eventually it can comes from empty fruit branch, activated carbon from palm kernel shell, and also the trunks and the fronds can actually considered to be converted into biochar. So looking into the industry itself, so there are some of the challenges in biochar production. So we can eventually convert all this biomass to biochar, but what are the problem or what is the challenges that we have? So firstly will be the nature of the biomass itself, okay, the physiochemical, so the physical and also the chemical characteristic of the biomass. So looking into just taking oil palm based biomass itself, we have empty fruit bunch, we have palm kernel shell, we have what else? We have palm kernel cake and so on. So their physical and chemical properties can say a bit different. So for example, you have palm kernel shell, probably it has high, still there are high oil content inside it compared to oil palm trunk, okay? So each biomass, their nature or the physical or chemical characteristic is a little bit different from one to another. So that could be a challenge in biochar production because sometimes you have to customize your operating condition to actually suit the biomass that you have. So looking at palm oil itself, but there are number of other biomass that is available. So for example, fruit peels might have different physiochemical characteristic. So each biomass has their own characteristic that we need to eventually study to optimize the operating condition and to give you or give us the desired biochar quality. So that is the number one challenge. Number two will be transportation problems. Okay, so most of the time when we see biomass, it is actually taking palm oil itself, we see the source of the biomass is at the production site. Okay, we don't have a good transportation system to eventually bring the raw biomass to a common facility to convert it to biochar. Okay, so most of the time biomass will be wet. Okay, it has a very high moisture content, for example 70 to 80%, and it will need drying process. Okay, because if you want to transport it, we need to kind of dry it. So a lot of pre-treatment work needed. For example, if we have large oil palm trunk, we need to chop it, we need to shred it, we need to grind it so that it's easier or more compact so that we can eventually transport it out. Okay, so that's why when it comes to palm oil mill, they will try to utilize the waste that they're generating in the mill itself. But what if we have a facilities like, for example, way out from the source? Because we look at the mills are scattered everywhere. We cannot have own facilities at the place because it's going to be very costly to eventually set up the place or the facilities to convert the biomass to biochar. So these are some of the challenges in producing biochar in a large scale. So since transportation is another problem, it also increased the production costs and also capital investment costs. Okay, so the cost to produce the biochar will become very expensive rather than discarding it. Okay, so there are lack of key players along the value chain. So biochar production is a bit costly, and commercialization in Malaysia itself is very new and is at a very early stage. Okay, so we are still in the research work, moving towards commercialization, but it's not really up to that scale yet. So these are the challenges in biochar production. So I just want to briefly introduce about this Biochar Association in Malaysia. So looking at the potential biomass has, eventually there's an association that came up or established in 2014 called Biochar Association Malaysia. Their mission is to promote the biochar production and also application in both agricultural and industrial sector. So their intention was to stimulate public awareness on the role of biochar as a potential of carbon sequester, a platform for idea information exchange, and also to promote the biochar industry in Malaysia. But looking at that, many key players are actually needed or need to work together. For example, researchers, authorities, business analysts, everyone actually has to work together to promote the advancement of biochar industry in Malaysia. That's on Malaysia. I'm just going to briefly go through a little bit of research that I have done. Although this is not the whole research that I do, I just want to relate one work that I did, because since we talk about oil palm biochar, I just want to talk a little bit more on the palm fiber that we can actually get from this oil palm industry. Okay, how this palm fiber can be converted into biochar. Okay, and how this biochar can be eventually used for another energy potential. So I'll be touching a little bit on the gasification process itself. So here I have two objectives. Okay, firstly was to characterize the biomass. Okay, the biomass that I'm referring to is the palm fiber, and then to eventually investigate the optimum operating conditions on the quality of the biochar that is being produced. Secondly is to study the behavior, especially the gasification behavior of the biochar that I produce under CO2 conditions. So as I mentioned, gasifying agent has many other steam, air, CO2, and so on. So this study was on under CO2 to see what is the behavior of the biochar under gasification, CO2 condition. So these were the two objectives. So let me move through what is the methodology. So this is the palm fiber. So the palm fiber biomass was first air dried. So once the moisture content has reached the air dried moisture content, it was eventually ground to a particular size of around 1 to 2 mm. Then this particular biomass or the palm fiber were subjected to pyrolysis experiment under high temperature. Okay, so this is the biochar after the pyrolysis. So basically our palm fiber is converted to biochar after pyrolysis experiment. So the raw palm fiber or the biochar eventually can be sent to know the heating value or the calorific value using a bomb calorimeter. Then we use a TGA, thermogravimetry analyzer, to eventually know all this proximate analysis, as I mentioned just now: moisture, volatile, ash, and also fixed carbon content. And there's another study that I did on looking at the behavior of the biochar under CO2 conditions. So TGA was eventually used to see how reactive the char was towards CO2. Okay. So the aim is eventually to produce syngases. All right, so this is the methodology, how a palm fiber can be converted into biochar through pyrolysis experiment and some other analysis that we have done to eventually characterize or find the properties of this biochar. So here you can eventually see the test that we run is eventually got two. One is the pyrolysis, secondly is the gasification. So when we want to produce biochar, we have to use the pyrolysis experiment. So I did use a reactor. Okay, roughly 20 grams of the palm fiber were eventually put into the pyrolysis reactor. And these are the temperature, residence time, and heating rate that we actually employ for pyrolysis. Okay, so we selected a few temperature to see what is the yield like: 300, 500, 700, and 900. Residence time was around 2 hours, meaning to say how long we are holding the sample in the pyrolysis reactor. And what is the heating rate that is employed? 10 degrees per minute. So this is the pyrolysis experiment. So once we get the biochar, what we do is eventually to study the gasification behavior. So here gasification itself is another thermal conversion process which happens at high temperature. Usually it's more than 600. So we subject this biochar to 600, 700, 800, 900, and 1000 degrees Celsius. Hold them for 1 hour, see what is the reactivity like. And heating rate over here is not really important because it just shows how fast the TGA heat up. One main thing that I never put here is the gasifying agent, where we use the CO2 as a gasifying agent. So our biochar reacted with CO2 to produce syngases at this different particular temperature that is listed over here. So let me just quickly go through the results that we got, feedstock proximate analysis. So before we do the biochar, we have the palm fiber feedstock itself. So this is the composition of moisture content, volatile matter, ash, and fixed carbon content in the biomass according to percentage of weight. Usually we use a TGA to determine this weight eventually, and different temperature to actually know what is the moisture content, volatile matter, ash, and also fixed carbon content. Then we have result from the pyrolysis experiment. So we subjected the biomass to 300, 500, 700, and 900. So from this table, we can eventually see what is the char yield like, okay, what is the oil yield like, and what is the gas yield like. Okay, so we can eventually see that when the temperature actually increases, our focus now is eventually to see what is the biochar yield. So the yield eventually decreases when the temperature increases. Okay, so when we do research, we probably want to find the right temperature to get the right yield, because we do not want most of it lost as volatiles eventually. So we want the carbon. So how much do we want at what temperature? So that could be an area of focus eventually. Then we have on the heating value or the calorific value. Okay, so since I mentioned this palm fiber biochar was used for the energy potential application, so heating value is kind of very important for us to eventually determine, so that we know what is the energy content in the biomass and also in the char itself. So we have biomass. So before it is reacted in the pyrolysis experiment, the heating value is around 16 megajoule per kg. Looking at the biochar that we have, for example, 300 degrees Celsius biochar, the heating value has eventually increased so much more to 23.06 megajoule per kg. So most of the time, any biomass that we use, roughly this is what we can eventually get. The raw biomass will have, usually it will be less than 20 megajoule per kg, but when it is upgraded in the pyrolysis, the value of heating value will be far more compared to the raw biomass that we have. But different temperature will be giving us different heating value. Okay, so from there we can eventually calculate what is the energy yield, because we know that the char yield, how much we are getting. So from the char yield that you get and from the megajoule per kg, the heating value that we get, we can eventually calculate what is the energy yield like. So by calculation, okay, 300 degree biochar eventually gives the highest energy yield compared to the others. So we can safely say that this is due to one is because we had the better yield at 300 degrees compared to other temperature, and also this heating value is kind of high, although it's not high as 500 and 700, but we try to correlate the yield and the energy content. Roughly we get this is the energy yield. So what happened after that? We have all the biochar, 300, 500, 700, and 900. We try to introduce it in the TGA. We react it with CO2 and see how it actually reacts with CO2. So here we eventually see what is the reactivity, char reactivity. Okay, so from the graph we can eventually see. Okay, I'm just taking one graph as an example. So I have char 300 over here. It was subjected to 5 temperature profile for the gasification behavior experiment. So we subject 600, 700, 800, 900, and 1000. Okay, so what we get end of the day. So this is the graph that shows the reactivity. So the orange line eventually indicates temperature at 1000, followed by 900, and also 800 is the green line. So we can actually see the reactivity is highest almost for all the char that we get. Okay, the pattern is kind of similar, where at 1000 degrees it reacts very vigorously. Okay, it gives the highest reactivity. Okay, followed by 900 and 800. Okay, and we can roughly say at 600 and 700 there is no reactivity found for this particular biochar. So from here, we can also see how fast it depletes in the CO2 condition. So we can actually see, like, within a few minutes spent in the TGA, the reactivity is like kind of slowed down already. So the highest reactivity was seen at 1000 degrees Celsius. The highest reactivity was seen in biochar for 900, followed by 300 biochar, 500 biochar, and also 700 biochar. The values are actually given here. At 900 degrees Celsius gasification temperature, within 15 minutes, all the sample depleted. Highest reactivity was seen for 900, followed by 500, followed by 300, and finally 700. So roughly what we can conclude is when it's higher temperature, it depletes fast, right? So if we are scaling up to have a scale up gasifier, we can eventually have batch gasification, because it just it just need short time to eventually complete reacting with CO2. So batch meaning to say, if we have sample, we have biomass, or we have biochar, we can do by batch. At one time, we put in the sample and then we try to get the syngas that is required. But what if we do not have much sample? Probably we might want to look continuous gasification, meaning to say the supply of this biomass or biochar is going to be continuous. So probably at lower temperature, for example 800, we can actually target for to complete because we can have longer time to complete the gasification. Okay, so we can eventually supply the feedstock continuously. So this is the conclusion that we can actually get from the char reactivity experiment. So as an overall conclusion for this particular research that I did on palm fiber is, palm fiber can be upgraded into solid fuel, okay, with a heating value of more than 23 megajoule per kg. Okay, as I mentioned, it was only 16 megajoule per kg for raw biomass. Then we can actually biochar produced has gasification potential because it has high reactivity. And what we can actually say is we need a temperature of more than 800 for the gasification to take place. So 600 and 700, there's no reactivity, so there's no point eventually subject the biochar at 600 or 700 because there's no reactivity found. So a temperature of 800 and more is eventually required for gasification to happen. And biochar produced at 300 degrees Celsius seems to have more energy yield and has highest reactivity at 1000 degrees Celsius gasification temperature. So it has around 0.19 per minute. Okay, so that's on my case study, the conclusion. So what is the way forward? So this is just a figure that I took from the internet to eventually see what is the number of publications on biochar itself in Scopus and also WOS since 2009. Okay, the final data that we have over here is up to 2019. So what we can actually see from here is, like, it's very clear that for the past 10 years, research in biochar has been kind of increasing drastically from around, I think, less than 50 publications in 2009 to around, how much is this? I think less than 5,000 publication last year itself. So it is increasing, it is going exponentially. Okay, so there are a lot of research on biochar that is going on for the past 10 years. So what is the way forward? We can eventually use all the available or abundantly available biomass, especially the underutilized in our country. Okay, so we are actually, Malaysia and Indonesia are kind of very much the same. We are agricultural nation. So if the biomass is not being tapped, it has to be kind of used or utilized for biochar production. So for biochar productions, pyrolysis seems to be a good thermochemical route, okay, from any biomass feedstock. And what we have is biomass and biochar are carbon neutral, and it reduces greenhouse gas emissions. So it's very, very green. It's very environmental friendly. All right. And biochar has versatile applications that can be actually explored further, especially for green applications. So when we talk about green application, eventually we can talk about energy, renewable energy. We can talk about environmental applications, which are on, you know, wastewater, water treatment, and some other emerging researchers. For example, green building materials, as I mentioned, biochar can eventually capture the carbon, so it can be sequestered and used in the construction materials. All right. So there are a lot of applications which are considered green that can be eventually used. Okay, so it has a lot of application. So with that, I will eventually conclude my presentation on biochar. So biochar is eventually black, but it has a lot of green applications that we can eventually try to look on, so that we have more researchers that is coming up. I just want to show my email over here. Okay, I would like to thank you for your time to listening to me, and I can be contacted at this particular email. Okay, I am very open to eventually have more collaboration with people from, Indonesia, because we like to go kind of outside Malaysia for international collaboration, for example. So if you are working with biochar, or if you suddenly think of some idea that comes about biochar that you can actually apply in your research, I'm very open for discussion. Okay, so as I mentioned, my work or my research has been on biochar and also biomass, more on this waste management kind of thing. And I do produce biochar in our lab eventually. So on the production part, on the characterization part, on the analytical part, I will be able to kind of fit in if you have anything that you want to talk to me about. So I hope there will be more collaboration, more sharing things coming up after this for both party benefits. Thank you very much. So now I will open for any Q&A after this. So Utami, back to you. I'm done with my presentation. Thank you.
Okay, thank you very much, Dr. Anurita, for a very interesting and insightful presentations. We are inviting to the participants. If you have some questions, you can type your questions in the chat feature. But Dr. Anurita, we already have a question from one of our students, Aida. Aida, do you want to ask your question directly to Dr. Anurita or Aida? Bapak dan Ibu silakan kalau misalnya ada yang ingin ditanyakan, bisa diketik di kolom chatnya atau langsung raise hand saja kalau mau bertanya. Nggak usah takut meski pakai bahasa Inggris, kalau mau pakai bahasa Indonesia silakan, bisa kami bantu untuk kami terjemahkan pada saat dibacakan. Mau pakai bahasa Banjar juga nggak apa-apa sih kalau misalnya mau. We can still translate it into English. Aida mana ya? Okay, so probably I will just read the question from Aida Fikria. Aida, okay. Aida asks you, what can we do to create better biochar? Should we focus more on the modification of the pyrolysis process, or should we focus on finding a better resources or the material or the raw material for the biochar? Okay, Dr. Anurita.
Okay, thank you, Aida, for your question. Okay, so I think everyone will have the same query as well. We can eventually create biochar from any bio-origin material, but the question will come back to us, which biomass that we want to use, and how are we going to produce, and where do you want to apply this biochar? So I will always maybe with the other way around, probably you have to specify your application area. For example, Okay, let me just see. Any kind of field, for example, if you're working on wastewater treatment, for example. So for the biochar to be used in the wastewater treatment, what could be the characteristic or the quality of the biochar that you might need to focus on to be applied in the wastewater treatment, for example. So from there, you can eventually find out, okay, I need this kind of biochar with this kind of characteristic. So you will eventually try to narrow down whether your biochar or the biomass can eventually produce the desired quality or not. Okay, that is one way of working around the research area that you have or the application that you have identified. Secondly will be, because I do get many questions elsewhere eventually. For example, I did, okay, just sharing only, I have quite a number of biomass that I've worked on. If you know pineapple peels, durian shell, banana peels and everything, okay, the question actually came back to me asking that, okay, it's very novel, it's very interesting that you can use any kind of peels for energy application, for example, but what is the availability like? Okay, so when that kind of question comes, you must know that when you're going to use as an energy application, definitely we need biomass that is kind of largely or the availability of the biomass. Okay, so probably you want to look into something that's in your country that is like, you know, highly produced but it's not being used anywhere, where if you want to mass produce your biochar, probably you have all the quantity that is available. So probably that way you can eventually identify what biomass that you want to use for your application. And once you identify, the characteristic is very important as well, and also the operating parameters is very important, because end of the day you do not simply want to do trial and error. Probably you will have your desired quality biochar that you will need for your specific application. Okay, so it can work both way, I will say. So it's best to eventually specify what is actually needed in the research. From there, identify what is the biomass that is eventually needed. So from there, you can eventually do some lab work to 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 increase the quality or to get the quality that you want for your application. Thank you, Aida. Any other questions, Utami?
Okay, thank you very much for your explanation, Dr. Anurita. So basically, we need to come back to our main intention on this research. Yeah. Okay, excellent. And then we also have question from Ibu Dwi Rasi. Bu Rasi, do you want to ask the question yourself, or you can, or maybe I should read your questions for you. So
please read the question for a moment, because I'm busy still and still and
okay. So
something to do.
Ibu Rosi is actually also a faculty member in the chemistry department in our faculty. So she asked, previously she had tried to make biochar from rice husk and applied it to see how the plant is going. Plant. And she was doing it for a scientific project for one of the high school in this area. So the results are quite good, even though the progression look faster. So I'm pretty sure that she meant the progression of the plant compared to when biochar is not being applied. So what are the good characteristics of biochar, especially if we want to apply it directly to the plants? Because you also have mentioned that one of the application of biochar is to enhance the plant development. So if we do want to use it for, some kind of additional fertilizer, can we say that it's also function as a fertilizer? What are the characteristics that we want to emphasize on this? Okay, Dr. Anurita?
Okay, thank you very much, Tami and Dwi, if I'm not mistaken, the name, sorry, for your question. Probably you have a good result before you convert into biochar. So you might be asking whether there's a need to eventually convert to biochar or not. But on the long run, we know that biomass will be eventually decaying. Okay, so when it decays, you might not have the result that you're looking for after it decays. So biochar, on the other hand, when it's turned into carbon, it can actually stay in the soil for thousands of years, for example. Somehow it will not have the stability that it requires, but there are a lot of researches that people are eventually doing to see what is the carbon stability or biochar stability when you apply in the soil. So most of the research are eventually going towards, thousands of years, it can actually remain in the soil. So we did mention that carbon has the carbon sequester ability and so on. So for example, if you're taking rice husk biochar to increase the crop yield, for example, so probably what are the things that you might want to eventually look is the whether it reduced the nutrient leaching and runoff or not. Okay, for example, we have biochar we are applying in the field. How much what do you call this nutrient it can eventually trap in the biochar itself. So some of the important things that you might want to look is the cation exchange capacity, CEC. Okay, so people who are working in the soil field, they will know what is that about. Okay, and what is the water retention capacity. So all these things are eventually important to lock the nutrient that we need, or maybe we can actually reduce the usage of fertilizer if biochar can do this work. All right, so probably the two important things that you might be asking is to check on the cation exchange capacity and the water retention capacity, whether it can hold the moisture, it can hold the nutrients that is required for the plant growth, for example. Yeah, so that will be my answer.
Okay, thank you very much. So water retention capacity is one of the most important factors from your explanation. Thank you, Dr. Anurita. And since we are also going live on YouTube and we actually have some people watching through YouTube, I have a question coming from YouTube. So the question comes from Shirley Haryanti. Biochar sangat berguna bagi tanah. Apakah biochar juga dapat berguna untuk menjernihkan air yang mengandung polutan? So basically, the question coming from Shirley Haryanti, and she asked, from your explanation, biochar besides being used for soil modifications and stuff, can we also use biochar to reduce turbidity in water? So how can biochar function as a coagulant and flocculant to reduce turbidity in water, and to automatically, can it also increase the quality of water? Okay.
Okay, thank you, Tami, for the question. Basically, I don't have an answer for that because what I have been doing all the while is producing biochar, and it is used for mostly industrial wastewater to treat the heavy metals. Okay, so when it comes to turbidity, I believe even industrial wastewater are highly turbid. Highly turbidity, and mostly when we look at agricultural wastewater, it will be highly turbid as well. So there are a lot of research that people or researchers have been doing on coagulant and flocculant. So it's two different process where I will say biochar will act more like an adsorbent, okay, to attract all these heavy metals. But when it comes to coagulant and flocculant, is a different mechanism altogether. Probably this is a very good area to eventually explore whether biochar can act as a coagulant and flocculant, and whether it can eventually treat the turbidity. Because I really don't have the right answer, but I feel it's a very important or niche area that we can actually explore, because I myself, I've never really applied biochar in the, as a coagulant, you see, but we can try, yes.
that answer actually leads to a very interesting new field of research, I guess. So
Yeah,
ya,
correct.
dari jawaban Dr. Anurita tadi, selama ini memang biochar seringnya digunakan untuk limbah industri, untuk industrial waste, karena berfungsi untuk menyerap atau mengabsorb logam berat. Akan tetapi kalau untuk khusus untuk menjernihkan atau mengurangi turbiditas, mekanismenya mungkin akan sedikit berbeda dan sesungguhnya ini merupakan peluang untuk bidang penelitian yang baru. So students who are now maybe trying to find out some topics for your final research, maybe this is a very good field of research. I've told you coming to this talk will be very valuable for your study. So I hope Ibu Shirley yang mungkin mengikuti lewat YouTube bisa mudah-mudahan jawaban tadi bisa menjawab ini ya, mudah-mudahan penjelasan tadi bisa menjawab pertanyaan Ibu. Terima kasih sudah bergabung lewat YouTube. And oh my God, we're almost at the end of the talk. It's almost like 1 p.m. It's been very nice hearing the talk from you, Dr. Anurita. Let me check. So, okay, and I'm sorry. So I think we're really running out of time. I'm pretty sure that actually a lot of you also have some questions, but as Dr. Anurita has told us before, she would be happy to answer your questions in other opportunity. You can send her emails. Is it right, Dr. Anurita? You can always send her questions through emails. So once again, I would like to thank Dr. Anurita to join us in this general lecture. Terima kasih juga kepada Bapak dan Ibu yang telah bersedia meluangkan waktunya untuk mengikuti kuliah umum kita pada hari ini, even though it's Saturday, walaupun hari Sabtu, even though it's weekend and maybe you'd rather do something else. We really appreciate you coming to this general lecture. We have more than 100 participants. Thank you very much, Dr. Anurita. So I think this comes to the end of this show, the end of this event. So once again, thank you very much. And also, I almost forgot. Usually we have like picture together. So maybe Bapak dan Ibu silahkan minta tolong mungkin bisa dinyalakan kameranya supaya kita bisa ada sesi foto bersama. Oke. Wah, ada yang dari bingung, Bapak jauh-jauh. Terima kasih sudah bergabung. And I also see from the presence list, we even have people coming from Universitas Nusa Tenggara, which is like very far from Lambung Mangkurat University, like it's in other province. So thank you very much for joining us today. Oke, silakan Bapak dan Ibu. Kameranya minta tolong, mungkin kita tunggu beberapa saat lagi. Tadi sempat Bu Isfatimah juga, Prof. Isfatimah sempat bergabung, saya senang sekali lihatnya.
Ya, tadi dari KJKI Bu Isfatimah mau gabung.
Okay, we actually, but maybe she was also busy with other activities. We have a professor coming from Yogyakarta joining us, Bu Isfatimah. Okay, so we will give you another 10 seconds to prepare your camera. Pak Azidi, terima kasih sudah bergabung. Yang paling awal datang, Pak Azidi, terima kasih. Kemudian juga tadi sudah ada Pak Urip, mungkin sekaligus mewakili Fakultas MIPA. Bu Oksi dari Biologi, terima kasih Bu Oksi. Mudah-mudahan ini ya, berfaedah, I hope. Okay, so I will start. We have like about, okay, we will have first session of photo taking. Intro, sorry about that. So put on your best smile on 3, 1, 2, and 3. Okay, that is for the people on the first slide, and then we're moving on to the next one. The next one, okay, Ica, silahkan kameranya. Ica, Rafsal, thank you angkatan 2020 yang sudah bergabung. We even have some freshmen joining this talk today. Okay, 1, 2, and 3. Thank you. And then probably this would be the last one. 1, 2, and 3. Okay. So I guess that's all for now. Once again, thank you very much, Dr. Anurita, for joining us today. Ladies and gentlemen who already joined us from the beginning until the end, thank you very much. Baik yang sudah bergabung melalui Zoom maupun melalui YouTube. Kita sangat appreciate sekali Anda sudah berhadir di sini. Mohon maaf atas segala kesalahan. Dr. Anurita, we do apologize if there's anything in this talk that is not to your liking. Mohon maaf. Itu saja mungkin saya mewakili program studi kimia Fakultas MIPA Universitas Lambung Mangkurat. On behalf of the Chemistry Department, Faculty of Mathematics and Natural Sciences Lambung Mangkurat University, this is the end of our general lecture. Thank you very much, and we'll see you in the next general lecture. We will keep you updated if we have another general lecture coming up. Thank you, everyone, and bye. Enjoy the rest of your weekend. Bye, Dr. Anurita. Thank you so much. Terima kasih semuanya.
Bye, everyone.
Thank you.
Thank you very much for having me.
Thank you, Dr. Anurita. See you.